So let's get started building out our algorithmic stablecoin. For this project, we're going to allow for anyone to be able to create a custom front end. So instead of using the Create Solana dApp scaffold, we're going to be using Anchor init for our backend and then creating a custom front end that's going to be able to connect to the Anchor program. So let's get started with the Anchor program. We're going to make a new directory for the stablecoin, and then we'll just navigate into that directory. And now we can use Anchor init. We'll name this stablecoin. And this is going to initialize an Anchor workspace for you to be able to create your Anchor program. So we'll let this build, and then we're going to open the project. Okay. So here you can see within our directory, we have the stablecoin. We're going to rename this just for convenience, that this is our program side of things, or our smart contract. And then we'll be able to have another folder for the front end. Okay. So in the program, you have your librs. So this is just a basic Anchor program that initializes, and we're going to customize this for our Anchor stablecoin. So let's first figure out how we want to design this. An algorithmic stablecoin maintains its value pegged to another asset. The core mechanism is going to involve adjusting the supply of the stablecoin to respond to market conditions. So we're going to have the goal of one stablecoin to be equal to 1 unit of our reserve token, which we're going to be considering our collateral throughout this project. So we'll need 3 things. We'll need the stablecoin, we'll need our collateral, and we'll need oracles to be able to understand the current market condition of our collateral. So we'll be able to deposit collateral and mint stablecoins, or withdraw collateral and burn stablecoins to respond to market conditions. So let's first get organized with our state. With Solana, all smart contracts are stateless, and we're going to store our state within accounts. So for this project, we're going to need 2 states. We're going to have a config of the overall stablecoin, and we're also going to want to keep track of the collateral. So let's write out the account states for both of those. Since this is going to involve a lot of different instructions, we're going to break up our program outside of just the librs and individually write all of the instructions. So inside our source, let's make a new file for state. And we'll do state.rs. And this is where we'll keep track of all the accounts that hold state. So we'll first import Anchor into this file. Now let's define our first account state. For this one, we're going to define the collateral. So let's do derive init space and debug. And then we'll define the struct. So this will be our collateral struct. So what do we want in our collateral state? Well, first we want to keep track of who the depositor is. So let's save our depositor address. And that will be a public key type. And now we need an account that's going to hold the SOL, which is our reserve token. So we'll do a SOL account. And that will also be a public key type. So this will be a PDA of the collateral account that allows you to deposit SOL. Now, we also need a token account for the stablecoin. So let's make this an associated token account. We'll just do token account. Will also be a pub key type. So we're going to want to be able to calculate health factor throughout this and allow for accounts to be able to be liquidated based on their current health factor. So to be able to calculate the health factor, we're going to have to keep track of the Lamport balance of each account. So we'll keep track of that here. We'll do Lamport balance. and that's a U64 type. And we'll also want to keep track of the amount of tokens minted. So amount minted is a U64 as well. And then, as always, we need to save the bump. So we'll save the bump for our collateral account and the bump for the SOL account, which is a U8 type. And then we're just going to keep track of if the account has been initialized or not. This is just to prevent overwriting of certain fields. So we'll do is initialized, and that'll just be a Boolean. So that should be our collateral account. If we need to save anything else as we're working through this, we can go back and add it. So now we'll go to the config account. So the next account we want to keep track of is our config account, and that's going to hold all of the global information of the overall stablecoin. So let's do, once again, derive init space and debug for our account. And we'll do the config struct. Now, first we need to know who the authority is. And this is going to be the overall authority of the entire stablecoin that has certain permissions. So pub authority, which will be a public key because that is the wallet address of the authority. We also want to keep track of the mint address. So this is going to be the mint account of the stablecoin, which is also a public key. Now, to be able to declare if an account is healthy or not, we're going to have global factors for liquidation, and that's going to be applied to each collateral account to understand if it's healthy or needs to be liquidated. So these factors are going to be, first, the liquidation threshold. So let's keep track of that. And that just determines how much extra collateral is required. Liquidation threshold, which is a U64 type. And now we'll need the liquidation bonus. So what this is, it's a percent of bonus land ports that's going to be sent to the liquidator as a bonus for processing the liquidation of an unhealthy account. And that's a U64 as well. And we spelled liquidation wrong, so let's fix that. Okay. And next is a minimum health factor. So if your health factor is below this minimum value, then it's saying that the collateral account can be liquidated. So minimum health factor. And then lastly, we need to save the bump. So we'll save the bump for both the config account and the stablecoin mint account PDA. So next, we're going to start writing our instructions for the overall program. And first, we want to be able to get these two accounts initialized. So let's initialize our config. And we'll go to source, and now we're going to make a new folder that's just going to be for instructions, and each instruction is going to live in here. Now in this, we're also going to separate the instructions a little bit more. So let's first just focus on the admin side of the stablecoin. So we'll make another folder for admin. Okay. Now within this folder, let's initialize our config. So we'll make a file for initialize config. Okay, so we'll start with use anchor. Okay, and now we're going to write the instruction for processing initializing our config. So we'll do pub fm process initialize config. So as always, the first parameter that needs to be passed through is going to be your context. So let's define that. And we'll just set up the whole function. Return our OK at the end. and we'll come back for the logic. So let's now define what our initialized config struct is going to look like. So this is always going to be using the derive account attribute. And then we'll define our struct. Okay. So this is going to state every account that is needed to be able to run the process initialize config instruction. So first we need the signer because that's who is going to be signing the instruction. And we'll just define that with the account. And it should be mutable because we're going to be initializing, so they're going to be paying rent. And the signer here is going to be the authority. So we'll just name the signer the authority. Now let's initialize our config account. So we can use the account attribute, use the init constraint. Now whenever you're initializing, you need a payer who's going to be paying rent, and that will be the authority, which is the signer of the instruction. Now, we always have to calculate space when we're initializing a new account because it's going to be taking up space on chain. So we can calculate space with a init space since we used a init space when defining our account here. So space, we'll start with our 8 discriminator and then just add in from the config struct a init space. And now we're going to just define the seeds. So we're going to have a lot of PDAs throughout this workspace, and we're going to have to be referencing the PDAs a lot. So you're going to have to memorize all of the seeds for each PDA to be able to derive them. So to make things easy, we're going to make a constant file to just keep track of everything in one space, and you can pull those constants in whenever you need to derive a specific PDA. So let's make a new file in our source folder and name that constants. We'll use anchor once again. And now let's just do pub const. And we'll do seed for the config account. Okay, and this is going to be U8. Okay. And we'll just set the seed for the config, just config, to make things easy. So B config account. Actually, we'll just make it config. Okay, now, since it's in another file, we have to be able to import it correctly. So we're going to use crate and do seed config account. And we're also going to need to pull in the config from our state file. And now we can just simply set our seeds to seed config account. Okay, and lastly, since we defined our seeds, we need a bump. And now we just need to name this account. So we'll do pub config account. And that will be an account with a lifetime specifier and the config struct. Okay, so now we have this config account. And we also need to think about what else needs to be initialized when you're creating the full algorithmic stablecoin project. And what we need is a mint account for the stablecoin. So we can actually mint an account through this initialize config. And we can do that by using the mint constraint within the account macro for Anchor. So we're just going to define the account here. And since we're initializing, we need to use the init constraint. We're initializing, so we once again need the payer. That will be the authority, which is the signer of this instruction. And then we'll also define seeds for this account. So we'll go back to our constants and make a seed for our mint account. And we'll just name this mint. Okay, so we can just set the seeds the same. and we'll import that with the use crate. Now we want to initialize the mint account. So when we're configuring the new mint account, we want to use the mint constraints to define how it's graded, who pays for it, how it's addressed. So let's just set first the mint decimals. Oh, actually we did the seeds, so we need to define the bump. So let's write that before we forget. Okay, so we initialize, we define the pair, we define the seeds and the bump. Now we can create the mint. So we'll do mint, define the decimals. And let's also make a constant for this because we'll be needing to use the mint decimals throughout the workspace. And we'll set that to 9. Go back to the initialize config, and then we're going to import the mint decimals. Okay, and then we'll just set the mint decimals to the constant we just created. Okay, now we need the authority, and we're just going to set that to itself here. So it'll be, the authority is going to be whatever we name this mint account. So we're going to name it just mint account for simplicity. Okay. And now we need the freeze authority, which is also going to be the mint account. And we need the token program, which we'll have to define as an account within the initialize config struct. So token program. Okay. So since we used mint account here, we need to make sure we name the mint account the same. So pub mint account. And this is going to be an interface account. And now because we specified the token program for the mint, we need to pass through the token program account. And lastly, because we are initializing new accounts here, we need to pass through the system program. Now we're using a few things from additional crates that we have yet to add to our cargo toml. So let's update our crates before we go any farther in writing the code. Let's look at what we have so far in our cargo toml, and that's just anchorling. So we're also going to want anchor SPL. So we'll just do cargo add anchor SPL. Oh, we have to cd in the correct directory. So because the entire anchor workspace is in this programs file, we're going to cd into program. And now we can run cargo add. Okay, so our anchor SPL was added. And now because we added an SPL, we have to update the IDL build. So we'll do anchor SPL, and then IDL build. And now, while we're here, there's one more thing that we're going to have to add, and that's going to be our Pyth Solana receiver. And this is for our oracles. So we're going to be needing to use an oracle to understand the current market price of our assets, and we're going to be using Pyth as our oracle for this project. So while we're here, let's just cargo add our Pyth Solana receiver SDK. Okay, so it looks like we have an error in our state. Let's just fix that before we move on. We're just missing a colon, little typo. And as you can see, everything here is a little bit grayed out. That's because it's not in our librs file. When we're using multiple files in our source file, we're going to have to make sure we import everything, we have our mod files correctly written. So let's first start with updating our lib to use the state. We'll do use state. Now, if you go back to the state file, you can see it's no longer grayed out. And we correctly had an import for this into our librs. And we'll do the same for our constants. Okay. And then let's set up our mod files in our instructions folder just to have everything set up for the future. So we'll do a file and instructions for mod.rs. And so far we've created an admin folder. So let's use admin. Okay. And then we need one more inside our admin folder. So we'll do a mod.rs here, and we'll do pub use initialize config, which is the file we just created. Okay, and then one more update, we have our instructions file, so we're going to make sure that that's being used in our librs as well. So we'll do use instructions and mod instructions. Okay. So now that we have all of our mod files set up correctly for this file path, now you can see everything is properly loading into our initialize config file. Okay. Now, one last thing we have to do is make sure we have all the correct imports for our SBL tokens. So you can see here, the mint is missing an import, so we're just going to import that. So we'll use anchor SBL. And this is from the token interface. And we want the mint. Okay, so let's review everything we have so far, and then we can start writing the logic for our process initialize config instruction. So for our initialize config, we have our signer, which is going to the authority of the overall stablecoin project. We have our config account, which is going to store all of the state needed for the general config of the stablecoin. We have our mint account, which is being initialized when processing this instruction. And then the mint account is using the token program, and we actually need to specify what token program we're using. So we're going to use token 2022 for this, and let's import that with our mint. Okay, and because we're using token 2022, this is a program. Okay, so we have the token program and we have the system program, and the system program is needed because we're initializing new accounts with this instruction. Okay. All of the account initialization takes place with these constraints that we pass with our account macros in our initialize config struct. So all we really have to do within the logic for process initialize config is save all of the information we want to the state of the config account. So let's do that. We're going to load in our context accounts config account, and we're just dereferencing that. So the first field of our config struct is the authority. Let's fill that in. The authority is going to just be, we can load in the signer from the context accounts. So we'll do ctx.accounts.authority.key, and that'll bring in the public key of the authority. Now we want the mint account. And since that's an account passed through our initialize config struct, we can just pull that in as well. So ctx.accounts.mintaccount key. Now we need the liquidation threshold, bonus, and minimum health factor. And these are all values that will be constants throughout the entire algorithmic stablecoin. We could do two things. We could have this as an argument that's being passed through that's a user input value. Or for simplicity, we can just save this as constants to our workspace. So let's save this as constants to our workspace. If you want this more configurable for future use, you can set this as arguments to be passed through. So let's do the liquidation threshold. And we're going to make this a constant. So we'll go back to our constants. And we're going to set the liquidation threshold to 50. So what this means is that it's 200% over collateralized. Now we're going to set the liquidation bonus. And we'll set that to 10. So what that means is that you have a 10% bonus land ports when liquidating an account. Now we'll set the minimum health factor. And we'll set that to 1. So anytime your health factor falls below 1, an account can be liquidated. Now we're going to import all of these. And we have a typo with liquidation. We'll fix that. Okay. Now what we have left is the bump for the collateral account and the bump for the mint account. So we'll do bump, and we can just grab that from context.bump dot, and then the account that we want. So we'll do config account. And it's bumps with an S, actually. There we go. And then the bump for the mint account. Okay, so that's everything we need to initialize the config. Now all we need to do is take this instruction and pull it into our librs. So we'll go to the librs, and we're going to delete the initialize instruction that came with our anchor init. And we're going to write our new instruction, which is just initialize config. And we're passing through the context. Okay, and all we can do is just pull in the function that we wrote from the other file. So process initialize config, and we're passing through the context. And we don't need the derive accounts that came with our preset. We can just delete that. And then we're going to clean up our initialize config file, and it looks like we had a strange import, so we're just going to get rid of that. All right, and now we're good to go. So we're going to finish up all of the admin functions. And one more thing that we're going to want to do is allow an admin to be able to update the config. So let's make a new file for update config. So this is going to be a lot smaller because we're not initializing anything. We're just updating an account that already exists. So we're going to use anchor to start the file. Now we want to go and update our mod file. So we'll do pub use update config, mod update config. Okay. Now we can start with our derive accounts. So what accounts do we need to be able to update the config of the config account? All we need is the config account. So it'll be a really short struct. We'll just do struct update config with your lifetime specifier. And then we're going to specify the account. So we'll do account. And now we have to make it mutable because we're updating the state of the account. So we have to define this as mutable. And then we need to be able to have the seeds and the bump because it's a PDA. So seeds, and since we save the seeds as a constant, we can just load in the constant and we don't have to remember what the seeds are. So seed from the config account. And then because we're defining the seeds, we need the bump. And since we saved the bump to the account state, we can just pull that in. So config account dot bump. And then we're going to name this account. And that's all we need. So let's make sure we have the right imports. We're going to use crate. And we want both the config and the seed config account. Now let's just write our instruction. So pub fn, we want to process update config. And the context, we're going to pass through the data structure that we just wrote. So we'll do update config. We want to return our results. Okay, so now what are we really updating? For our case, the only thing that we're gonna need to update in the config account state is the minimum health factor to be able to test liquidation. You can allow for this to be more configurable by updating more parts of the state, but we're just gonna update the minimum health factor for our use case. So since we wanna update it, we need to pass through as an argument the new minimum health factor that we wanna update to. And then we're going to load in our config account from the context. So we'll do let config account equal, and we'll do a mutable reference to the account. And that's our config account. And now all we're doing is updating the minimum health factor to the new minimum health factor that's being passed through. And then we can just return our OK, and we're good to go. Okay. Now we're just going to take this function and pass it through our librs. So we'll update our librs to have another instruction. So we'll do pub fn update config, pass through the context, and this will be the update config context. We're going to pass through the minimum health factor, and then we're just going to pull in the process update config function that we just wrote in our other file, and then pass through the two arguments that we need. And that's everything we need for the admin section. So we can just review our files. They all look good to go. We updated our mod file and our update config. So now because we want to adjust the supply of the stablecoin to respond to changes in market conditions, we're doing two main actions: deposit and mint, and burn and withdraw. So let's focus on the deposit section first. We're going to make a new folder in our instructions for deposit. Now we need the mod file for our deposit folder. Okay. And now we're going to make a file for the instruction that we want to write, which is deposit collateral and mint tokens. So we'll do new file and name that. Okay, so now we'll write the instruction for deposit collateral and mint tokens. And let's start with the struct for our context. So we're going to use anchor. And then we're going to derive accounts to define our struct. Okay. So we'll just name this deposit collateral and mint tokens. Add our lifetime specifier. Now let's go back, make sure we have our mod file updated. We want to use the file we just created, and then mod for the file we just created. Okay. And then we're going to update, since we created a new folder for deposit, we're going to go back one for the instructions, and we're going to update the mod there. So we'll do pub use deposit and mod deposit. Okay. So now let's define all of the accounts that we need for our deposit collateral and mint tokens instruction. So first we're going to start with the signer of the instruction, and that is going to be the depositor in this case. So we'll name that. We're going to need the config account to be able to access the global config for the stablecoin. So let's pass that through as well. Now we're going to have to define the seeds here since it's a PDA. And because we saved this as a constant, we can just pull in the constant for the seed config account. We define the seed, so we need a bump, and the bump was saved to the config account, so we can just pull that in. And now we want to do one constraint check, and we want to make sure that this config account has the correct mint account. So we're going to just do a check has one equals mint account, and we'll have to pass through the mint account as an account in the struct as well. Now we'll do pub config account. There we go. And now we want to update all of our imports. So we want the create for the seed config account constant. We want to import the config as well. So we're just going to add that. And now we're getting an error here under the mint account because we haven't stated that account yet. So let's actually go and write that next. Okay. So now we want to be able to keep track of the collateral. So we want to load in the collateral account so we can update the state as needed. So let's add that as the next account. Now here, the collateral account will be specific for the user. So we're actually going to want to use init if needed because we're not sure if the user has a collateral account or not. So we're going to have to update our create. So let's do cargo add. We already have anchorling, but we need to make sure we have this feature for init if needed. So we'll do anchorling features, init if needed. And what this does is it just checks if the account is already initialized. If it is, it's going to ignore that constraint and continue with the rest of the logic. If it's not, then it's going to initialize the account. So we'll do init if needed. And then because we're potentially initializing, we need a payer, and the payer is going to be the depositor in this case. We need to define the space if we're initializing. So we'll do space is equal to the 8 discriminator plus we're going to load in the collateral struct for the account and then use init space. Okay. Now we just need to define the seeds. And in this case, we're going to use the seeds for the collateral account. But we also want to specify that this is for a specific user. So we're going to add in the depositor key. Okay. Now we need the bump since it's a seed. And then we're just going to define the account. So collateral account. Okay, now let's update our imports. We'll import the mint, and that's going to come from token interface. So we'll do anchor SPL token interface mint. And now we also want the seed collateral account imported, which we haven't defined yet. So let's go back to our constants and define our seed collateral account. And we'll just make that collateral. Okay, now it can be imported. Now we need to also import collateral from our state file. And now we have an error under collateral account, and that's because we're potentially initializing a new account on chain. So we need to pass through the system program to do that. So we'll just add in the system program there and let that error go away. Okay. So now let's think, what are we doing here? We're depositing collateral and we're minting tokens. So we need accounts that are going to be holding those tokens. So for our deposit collateral, we need a SOL account that's going to have tokens to be able to send. We're also going to need a token account to be able to hold the stablecoin tokens. So let's add both of those accounts. We'll do account. It's going to have to be mutable because we're going to be transferring tokens. So we need to be able to change the state. And then we'll need to define the seeds for this. So we'll do seeds for a SOL account. And let's go back to our constants and define what that is. Okay, and we'll just name that SOL. And then we'll update our import here. There we go. And then because this is user specific, we're also going to want to add the depositor's key into the PDA. So we'll do depositor key as a ref, and because we have seeds, we need the bump. Okay. Now we can just define this for the SOL account. And since this is just holding LAN ports, it's going to be a system account. There we go. And now we need the associated token account for the mint of the stablecoin. So we'll add that. And here we're going to use a init if needed as well, because we're not sure if this depositor actually has an associated token account for the SPL token mint that we need. So we'll add in accounts and we'll do a init if needed. And the reason we didn't need to do a init if needed for the SOL account is because the depositor is depositing SOL, so you know that they have the SOL account. And then because we're potentially initializing, we need a payer, and that payer is going to be the depositor. And then this is an associated token account, so we're going to use the associated token constraint for this account. So for the associated token, we need to specify the mint. And the mint is just going to be, we can pull from the mint account that we already defined earlier. And then we'll do the authority, and the authority is going to be the depositor. And then we also need the token program. So associated token, token program. And then we'll just pass through the token program as an account as well. Okay, so now let's define this account, and this is just a token account. And since we're using interface tokens here, this will be an interface account. Token account. Now, because we have the token program here for the associated token, let's pass through the token program as an account. Okay. So we'll do program, and then to stay consistent, we're going to be using token 2022 throughout this workspace. So token 2022, okay. And then because this is an associated token account, we also need to pass through the associated token program. So pub associated token program. This is a program. And then associated token. Okay, and then we'll update our imports. So this is coming from the token interface. And then token 2022 is coming from the token interface as well. Okay, so let's review what we have so far. So we have the signer, which is the depositor. We have the config account, which is holding all of the global config information for the algorithmic stablecoin. we have the mint account, which is the mint of the stablecoin. We have the collateral account, which is holding all of the collateral information for this specific depositor. We have the SOL account, which is the SOL from this depositor, and then the associated token account for the stablecoin. We have the token program, associated token program, and system program. Okay, so there's one more thing that we're going to need here, and that is our oracle, because when we're depositing collateral and we're minting tokens, we want to be able to calculate the new health factor, and that's dependent on the current market value of these tokens. We can figure that out by using the oracle. So we're going to do price update, and this is an account. We'll use the lifetime specifier, and this we're going to use price update v2 from Pyth. Okay, and then we'll want to import that from the Pyth Solana receiver SDK. Okay, so you can see, oh, I went back too far. Hold on, let me just re-import this. There you go. Okay, so you can see we have an error here under the derive accounts, and it's saying that there is an owner field not satisfied, and that's actually because when we wrote the mint, we're using the wrong account. So we're using token interface for the rest of our tokens throughout this struct, and here we're just using an account. So we want to update this to interface account. Okay, and now the error goes away. And then there's one more update we're going to want to make to the struct. We're going to use a box around the config account. And what this does, it's just a smart pointer used for heap allocation. So it'll just help manage this data structure. So now everything's good to go for all of the accounts that we need to sign the instruction to deposit collateral and mint tokens. Now let's start writing the logic out. We'll go down here and write pub fn process deposit collateral and mint tokens. Okay, so we'll first pass through the context, which is the struct that we just defined above. And now we're going to need two additional arguments. So it's going to be the amount of collateral that you want to deposit and the amount of tokens that you want to mint. So those are going to be two U64 types. Okay, and then we'll just get our result. And then we'll return our OK at the end and then go back and write our logic. Okay, so now let's first pull in the collateral account so we can update the account state based on the amount of collateral that we're depositing and the amount of tokens that we're minting. So we'll first do let collateral account equal, we'll have a mutable reference, and we'll pull in the collateral account. Now we're going to update the Lamport balance and the amount of tokens that are minted. So we'll do collateral account dot Lamport balance is equal to, and we're going to gather the amount of Lamports in the SOL account. So you can do that by loading in the account from the context. So we'll do ctx.accounts.SOL account. And then you can just grab the Lamports. And then we're also going to add in the amount of collateral to that because that's how many Lamports we're depositing. Okay, and now we want to update the amount minted. So we're going to add the amount to mint to the amount minted in the collateral account. So we know for the collateral account, we use the init if needed. So this account could be initialized or not. If it hasn't been initialized yet and we're initializing it when running this instruction, we want to update all of the information in the state to initialize the account. So we're going to first check to see if the account was initialized. So we'll do if the collateral account was not initialized. So if the Boolean is still false, we're going to update to true, and then we're going to set all of the fields in the state. So we'll set the depositor, and that is going to be the key from the depositor account. Okay. And then we want to set what the SOL account is. And that will just be the key of the SOL account. Okay. We also want to set the token account, and that'll just be the key of the token account. And then we want to set the bump of the collateral account and the bump of the SOL account. So now we have the state initialized if the collateral account hasn't been initialized yet. Now there's 3 things that we're going to have to do when we're running this instruction. We want to first check the health factor, then we want to be able to deposit SOL, and then we also want to be able to mint tokens. So let's actually take this logic out. We're going to extract it into another file and then pull those functions in. So we're going to go back to the deposit file, and we'll make a utils file. Okay, so here we'll use Anchor. We want to update our mod file. Okay. Now let's first think about the utils that are related only to deposit, because when we're checking the health factor, we're going to have to do that with withdrawal as well. So we're actually going to extract that one level farther. So let's first focus on deposit. And to deposit, we need to be able to mint tokens and deposit SOL. So let's first write the function to mint tokens. Okay, so how do we mint? We're going to use mint2 from Anchor SPL. So we can import that. So from Anchor SPL, we're going to use token 2022 and the mint2 function. So you can see this function takes 2 arguments. The arguments are the CPI context. So we're going to first write out what our CPI context is. And now when we mint tokens, it's coming from the mint account. So if you remember when we created our mint account, it has a PDA. So we're actually going to have to use our signer seeds here to be able to sign the CPI. So we can do that with new with signer, and we're going to have to define what those signer seeds are. So let's go back up here and define what our signer is. So let signer seeds. And now we're going to explicitly define the type because it's a little complicated of what the type is for signer seeds. So it is 3 references. So we have 1, 2, 3, and then a U8. Okay, so we can write that with just reference, and we're going to import the seed for the mint account. So we'll import the crate, okay? And then for the signer seeds, we also need the bump. So let's state the bump. And we'll just pass the bump through as a parameter since we have the bump in our deposit collateral and mint tokens function. So we can just pass that through this function as an argument. So we'll do bump, which is a U8 type. Okay. Oh, put that in the wrong spot. We'll fix the formatting. Okay. So bump is a U8 type. Okay. So those are our signer seeds. So now we need, for the CPI context, this takes in 3 arguments. So first we're going to need the program. We can define that. So we'll do the token program to account info. Since we have the token program in our instruction, we can pass that through as an argument. So this will just be token program. And it will be of type program, and we're using token 2022 here. Okay, so we want to import token 2022. So there's our program. Now we need the accounts. So we're actually going to use the mint2 struct. Okay, so mint2, we need to pass through the mint, the to, and the authority. So the mint is going to be the mint account, and we have the mint account in our instruction, so we can just pass that through as an argument as well. So we'll add that here, mint account. Now this is an interface account. We'll do the lifetime specifier and then the mint type. And we're going to have to update our import to have mint. So we'll import mint. And the mint is coming from token interface, so right here. So now we can just define our mint as the mint account that's being passed through. So we'll do mint account to account info. We'll need our to fields. So we're minting tokens from the mint account to the token account for the user. So this is their associated token account. So we can also pass that through since we have that in the instruction. So we'll do token account. And this is an interface account, token account. We need to update our import with token account. And that is coming from token interface. So for 2, that will just be our token account to account info. And then lastly, we need our authority. So when we created the mint account from our initialize config instruction, we specified that the mint account authority is itself. So here we're just going to put the authority as the mint account. Okay, great. And then lastly, we need to just pass our signer seeds through. Okay, and we'll update the import to include mint2. And mint2 is coming from token 2022. Okay. And now let's see. We're missing one more parameter from the mint2 that we imported, and that is the amount. So we're just going to add in the amount of tokens that we want to mint, and since we're gathering that from the instruction as well, we can just pass that through as an argument. So amount is going to be a U64 type, and then we'll put amounts here for how many tokens we want to mint. Okay, so there's our function to be able to mint tokens. Now, the last thing we need for the deposit section is being able to deposit SOL. So let's write a function to deposit SOL. We'll do pub fm deposit SOL. Okay, so when we deposit SOL, we're not minting and burning tokens, we're just making a transfer from a SOL account into another account. So this is actually just going to be a CPI for a transfer. So we can import transfer. And that is going to be a with the CPI context. And here, it's not a PDA, so we don't need to do new assigner. We can just do new. We'll define the program, and since we're just transferring LAN ports, it's going to be the system program. And we have the system program because we're passing it through as an account in our context for our instruction. So we can just add that as an argument here. Your system program. It's going to be a program system. Okay? So the program here is just system program to account info. And now we need the transfer. So here we just need the transfer, and the transfer is from and to. So from is going to be the account that we'll pass through. So from will be the signer because we're depositing from the signer into an account. And then we'll have to is going to be a system account because it is the account holding SOL. Okay. So from, we'll just do from to account info, and then to, we'll do the same. And then we need to update our import to include transfer. And this transfer is going to be coming from the system program. So anchorling system program transfer. And we also want to update this import for transfer. And this will also come from the system program. Okay, and we're just going to clean up these imports because VS Code did it a little funny. So let's get rid of this. There we go. And then lastly, for the transfer, just like for mint2, we need to specify how much. So in this case, it will be LAN ports. So we'll just do amount, and we're going to pass through the amount as an argument for this function. So amount will also be a U64 type, and there's our function to deposit SOL. Okay. So let's pull those two functions back into our deposit collateral and mint tokens instruction. So we can just very easily import deposit SOL. So we'll update our crate to use deposit SOL. Okay. And then we'll just update the parameters that are needed. So it's from, to, system program, and amount. So the SOL is going to be coming from the depositor. So we'll load in the context.accounts.depositor. It's going to be going to the SOL account. So we'll load that account in as well. So context.accounts.SOL account. And then the system program is the account that we passed through already in our context, so we can just load that in. So context.accounts.system program. And then lastly is the amount, and the amount is the amount of collateral that's being passed through this instruction. Okay, so that's everything we need for deposit SOL. And since this is a function, we're going to unwrap it. So now that we deposited, we're going to be able to mint. So we'll import our mint tokens function. And we're going to update our imports here to use the crate for mint tokens. Okay, so this function takes in, let's hover over and see. It takes the mint account, the token program, the amount, and the bump. Okay, so let's pass that all through. So we'll load in the mint account, the token account, the token program, and now the amount is the amount to mint that was passed through as an argument for this instruction. And then lastly is the bump, but this bump is the bump for the mint account. So we're going to update what Copilot suggested, and we want to load in the context.accounts. And we saved the mint account bump into our config account. So we can just pull in the config account and grab the bump for the mint account. Okay, there we go. And we unwrap that function. Now, the only thing we have left to do for this instruction is checking the health factor before we actually deposit and mint tokens. So we're going to back up a little bit and create a util for all of the instructions that allow checking the health factor. So in our instructions folder, we'll make a new file for utils. We're going to update our mod.rs. Now we'll go back to the util file, and we're going to use anchor. Okay, so let's first calculate the health factor. So we'll do pub fn, calculate health factor. And for this, to be able to calculate the health factor, we need the collateral to understand how much SOL is deposited, how many tokens have been minted. We also need the config account to be able to get the global config information, which includes things like the liquidation threshold and the minimum health factor. And we also need the price feed from our Pyth oracle to be able to get real-time price data for each asset. So first, let's pass through collateral. And this will be an account for collateral. Now we'll pass through the config account, which is also an account for config. And then we're going to pass through the price feed. And this is also an account, and this is coming from the Pyth price feed update. So price update, we're using v2 in this project. Okay. And then our result here is going to be a U64 type because we want the value of the health factor to be returned. Now we need to update our imports. So we need collateral. We need the config. And then we also need the price update v2, and this is coming from the Pyth Solana receiver SDK. So now we're going to make the calculations for the health factor. And essentially, at a high level, the health factor is just going to be your collateral adjusted for the liquidation threshold divided by the amount minted. But we're going to have to do a little bit of conversions before doing that. So first, we want to get our collateral value in USD. So to do that, we're going to want to understand the SOL price in USD, and to get that, we're going to need the Pyth oracle. So let's first define this variable. So collateral value in USD. Okay, just for simplicity, we're going to make this a separate function so it's more readable. So we're going to do get USD value and write this underneath. So all you need to be able to get your USD value is the Lamport balance of the collateral account, which is how much SOL you have, and you need the price feed for SOL from the Pyth oracle. So we'll use that as the two arguments for this function. So it'll be from the collateral account. We need the Lamport balance. And then we also need the price feed. And now we're going to unwrap that. So let's go down here underneath this function and write another one to get the USD value. So as we just explained, we're passing through the amount in Lamports, which is a U64 value, and we're passing through the price feed, which is an account of the price update v2. Okay, we're going to delete what Copilot just suggested. So we're returning a result of a U64 because this is a collateral value, so it'll be a U64 type. First, we need the feed ID. So let's feed ID equal, and you can use this function that comes from Pyth. So to get the feed ID, we're going to have to import a hex value, and then we can use a function from Pyth to get the feed ID from the hex that we import. So let's first import this function from Pyth. It's just get feed ID from hex. Okay. Now we'll want to update the import here. So this is coming from the Solana Pyth receiver price update, and we'll just add in this function. So it's get feed ID from hex. There we go. Now we'll need to update the parameters here. So this function takes one argument, and that is going to be the feed ID. So let's go to our constants and figure out what this ID is for our Pyth price oracle. So we'll go back to constants. We're going to add in the feed ID. And this is just a stir type. So feed ID stir is equal to, okay, now let's get this ID. So you can go on the Pyth website and we can go here. So price feed IDs are all listed on the Pyth website. We're gonna click on the drop-down menu and find Solana stable. And now we want the price feed ID for Sol. So you can see here for Sol USD, this is the price feed. So let's copy this over and we're gonna save that into our constants. Okay, we'll go back to our editor and paste that in. Okay, and there's our feed ID. So we'll go back to utils and we can import the feed ID here. And then we'll unwrap that. And now we can take this feed ID and calculate the price. So we can use another function from Pyth. So we'll do let price is equal to, and we'll do the price feed. And we'll do get price. And we want to do no older than. And this is just making sure that you're not getting a stale price. So no older than. Okay. And we can do clock get to get the current time. And now we need a maximum age. So let's set this as a constant as well. We'll go back to our constants. Pub const maximum age. This will be a U64 type. And we'll just set this to 100. So what this is saying is it's allowing the price feed to go up to 100 seconds old. After that, it becomes stale. So we'll do 100. And we want to update our import. So we're going to use the crate for the maximum age. Okay. And then lastly, we need the feed ID. So we just got the feed ID, and now we'll just want to reference it. Okay. And then we'll unwrap this. And there's our price. So now we'll implement a little bit of error handling. We're going to want to make sure that the price is a positive value before we start running calculations with the price. So we're going to use require, and we'll take the price. And now the price is a price type. So let's actually take a look at what the price type is. So the price is a struct, and it has the price, the conf, the exponent, and the publish time. So we just want the actual price. So we're going to do price dot price to get the price value. And we want to make sure that this is above 0. Okay. And if it's not, we're going to return a custom error. And that will be invalid price. Now, this is the first error we've written so far in our workspace, so we're going to actually create a file for all of the errors that we're going to be writing. So let's go back to our source folder, and we're going to make a new file for error.rs. Okay. Now we're going to use anchor, and then we're going to use the error codes, and we'll make an enum of custom errors. Pub enum custom error. Okay. And now we're going to take the error that we just wrote, which is invalid price, and set that in our custom error code enum. And then we just want to define the message. Okay. And now, as you can see, this is grayed out, so we need to update our mod.rs to be able to recognize this error file. So we'll go to lib pub. We'll just use error mod error. And now we want to use the crate for the custom error. So let's import that. Okay, good to go. Okay, so to be able to get the price in USD, we have to take into consideration that we're using Lamport here. So we want to use a Lamport adjustment. So let's do let price in USD. We're going to take the price from the price struct. We're going to cast as a U128 for precision. And now we want to multiply by the decimal adjustment. So let's go back to our constants, and we're going to define what this adjustment is. So we'll do price feed decimal adjustment. So this is a U128 type. And this adjustment is just going to be 10 because the price feed returns 10 to the 8th, and we want to multiply by 10 to reach Lamport's, which is 10 to the 9th. Okay, so we'll go back to our utils, and we're just going to multiply by this constant. And then we have our import was updated. Okay, so now we have the price in USD, and we want to be able to calculate the amount in USD. So this is just converting from our Lamports to our SOL value. So we'll do let amount in USD. We'll dereference amount in Lamports. Cast as a 128 for precision. We're going to multiply by the price in USD. And then we want to divide by how many Lamports per SOL. So this is another constant. Okay. And that'll be cast as a U128 as well. And then we updated our import for Lamports per SOL. So now that's our USD value. So now we can just return that. And we're going to cast as a U64. Okay. Okay, so now that we have this function, we can go back to calculating the health factor. So we now have the collateral value in USD, and we're using the get USD value that we just calculated. Now we want to adjust the collateral value for the liquidation threshold. So all we're doing is multiplying by the liquidation threshold, and this just requires over collateralization. So let's collateral adjusted for liquidation threshold equal, and we'll just take collateral value in USD, multiplied by the liquidation threshold that is saved to the config state. So, and I can see I have a typo here, so let's fix config. Okay. And then you want to divide by 100 because it is a percentage. So now to get the health factor, it's the collateral adjusted for the liquidation threshold divided by the amount minted. But we want to make sure that we're taking into consideration divide by 0 errors. So there is potential that someone has an account with 0 amount minted. So let's check that first. So we'll do if collateral dot amount minted is 0. We're going to return, and we'll just print the message of health factor max. Okay. And we'll return the max value. Okay. Now, if it's not a 0, we're going to calculate the health factor by dividing. So we'll do let health factor equal, and it will be the collateral adjusted for the liquidation threshold divided by the amount minted. And then we can just return the health factor. Okay, so now we calculated the health factor. So now we have the health factor, but what do we do with it? So we're going to make a function to check the health factor to see if an account is healthy or not. So one last function here in our utils, we're going to do pub fn check health factor. And this is going to take in the same thing as calculating the health factor. We need the collateral. Let's actually just copy it to make it easier. Okay. We'll return the result. We're going to delete what Copilot suggested. Oops. There you go. Okay. So all we're doing is loading in the health factor. So the health factor is calculated with the function we just wrote. Okay. And now we want to require that the health factor is above the minimum health factor. So require health factor is greater than or equal to config dot minimum health factor. Okay. And we're able to just load this in from the config state because we saved this earlier when we were initializing the config account. And if it's not, then we're going to return a custom error that you are below the minimum health factor. Okay. And then we're just going to return an OK. And now we have to update our custom error enum to include this new error that we just wrote. And we'll add a message. And we spelled calculate wrong here, so let's just fix that. Lots of typos. All right, so these are all the utils we need to be able to calculate the health factor. Now we can just take this and import to our deposit function. Okay, so we want to be able to calculate the health factor before we actually execute the deposit and minting tokens. So we'll add this function here, and we'll do check health factor. And then we'll make sure that we import. So we'll use crate check health factor. Okay, and now we're going to check the parameters here. So it takes in the collateral, the config, and the price feed. So we'll update those arguments. Okay, so the config account. Okay, Copilot did this a little backwards. So let's fix that. It's first the collateral account. Okay. Then it's the config account. And then it's the price update. And then we'll just unwrap that. And that is everything we need for depositing collateral and minting tokens. So now we can take this instruction and pull that into our librs. We'll go back to the librs and we'll make a function for deposit collateral and mint tokens. And this takes in the context, it takes in the amount of collateral, the amount to mint, and it's using the function that we just wrote here. Okay, just a recap of what we've done. We've initialized the config, created our config account, our collateral accounts. We've added the instruction to be able to update the config. We've created an instruction to deposit collateral and mint tokens. So now what do we have left? We need to be able to withdraw collateral and burn tokens. So do the reverse of what we just did. So let's make another folder for withdrawal. Since we're making a new folder, we're going to need another mod.rs. Now we're going to need a file for withdrawal. So we'll do, we're redeeming collateral and we're burning tokens. All right, so we're going to use anchor. Now let's first define the struct for our context. So here it's going to be very similar to our previous struct because we'll need almost the same accounts. So let's do derive accounts. We'll name our struct redeem collateral and burn tokens. Okay, so the first account we're going to pass through is the signer. And this will be the depositor because they're redeeming collateral that they've deposited already. We'll make this mutable. So this will be a signer. Okay. Now, just like for deposit, we need to be able to calculate the current price of these assets. So we're going to pass through our price update. And that will be the price update v2 from Pyth. So let's update our imports to make sure it has that. So we want to use the Pyth Solana receiver. And then price update v2. Now we're going to need both the config account and the collateral account from the depositor. So we can load in the account for config. And this, since it's a PDA, we need to define the seeds. And we'll just take the seed config account that we've already saved to our constant. And then we also need the bump, and the bump was saved to the config account. So we'll just pull that. And then lastly, we want to make sure that this config account is using the correct mint address. So we're going to add a constraint to verify that. So we're going to do has1 mint account. Okay. So now we'll define this. This is the config account. This is an account type. So now we'll also need the collateral account. The collateral account we're going to need to make mutable because we're going to be updating state changes. So we'll do mute. And then we'll also need the seeds because it's a PDA. And this is the same as the collateral account that we use for deposit. So it's both the seeds of the collateral account and the depositor's public key. So we'll add seed for collateral account, and then we'll do depository key as ref. Okay. And because we did the seeds, we need a bump. And the bump is saved to the collateral account. And then we're going to do 2 checks on the collateral account. We want to make sure the collateral account has both the same SOL account that's being passed through the struct and the same token account that's being passed through the struct. So let's add those two constraints. So has one equal to, we'll do the SOL account, and then has one token account. Now, because we're using this constraint, we need to make sure we're passing through both the SOL account and the token account in the struct for it to be able to reference it. So we'll finish defining the collateral account, and then we want to update our import since we use these constants. So we're going to use crate, and there we go. And now you can see some things aren't fully loading, and that is because we need to update our mod file. So let's go back to our mod and make sure we have everything properly updated. So pub use, we want to use the redeem collateral and mint tokens file we just created. Sorry, we're burning tokens, not minting. And burn tokens, and then mod, okay? And then we also want to update, we're going to go back one file, and we want to update our mod file in the instructions to use the withdrawal folder that we just created. Okay, so now everything's updating and returning proper errors that we want to see as we're typing this code out. Okay, and you can see these errors, because this constraint needs to have all of these accounts pass through to be able to do the check, it's notifying you that we haven't passed these accounts through the struct yet. So we're going to do that before we finish. Okay, so we have the collateral account. So next, let's do the SOL account. And the SOL account, because it's LAN ports, it's actually a system account. Okay. And now we need the mint account. And both of these accounts are mutable because the balance of the accounts are going to be changing. And the mint account is an interface account with the mint. And now we need the token account, which is also an interface account. Okay. And then lastly, we need the token program and the system program. So we'll pass those through. And the token program, we're using token 2022 here. Now we just need to update our imports. So we have the mint, and the mint is coming from token interface. We have the token account, which is also coming from token interface. And token 2022. Okay. And now let's just update our imports. We accidentally imported the seed for the SOL account, which we don't need here. Okay, so this is all of the accounts we need for this struct. Now we can go on and write the instruction. So pub fn, we want to process redeem collateral and burn tokens. Okay. As always with an anchor instruction, we want to pass through the context first. And this is the redeem collateral and burn token struct that we just defined above. Okay. Great, and now just like the previous instruction, we want to know how much collateral and we also want to know how much to burn. So we'll pass those two values through as well. So amount of collateral, which is a U64, and then amount to burn, which is also a U64. Okay. All right. Now let's start writing the logic out. So first thing we want to do is update the state in our collateral account reflecting the tokens that we want to burn and the tokens we want to redeem. So we'll load in our collateral account, and then we're going to update the collateral account LAN port balance So we'll grab the LAN ports from the Sol account. So context.accounts.sol account. And then we're going to subtract the amount of collateral that we specified. And now we just want to update the amount minted. So we'll do collateral account, amount minted, and we're just subtracting the amount to burn that was specified. Okay, now just like the last instruction, we want to be able to check the health factor. So we're just going to import the same instruction that we wrote earlier. So we'll do check health factor. Let's import the health factor so we can see all of the arguments that are required. We're going to update from our crate. We want to check health factor. Okay. Now that that's updated, we can hover over this. So the first account is collateral, then config, then price feed. So and ctx.accounts.collateral account. Okay. And then we want the config account, and then we want the price update for the price feed. And then we'll just unwrap this. And this should be commas, not semicolons. Just fix our typos. All right, there we go. So there's our first check for the health factor. So we have two more functions that we want. We want to be able to burn tokens and then also withdraw SOL. So we're going to write those functions in another utils file just like we did for deposit. So we'll go back to our withdraw, and we're going to make a new file, and this will be utils. We're going to update our mod file to reflect that. So we want pub use utils and then mod utils. Okay. Now we'll go back to our utils. We're going to use anchor. Okay. Now let's write the function for withdrawing SOL. So pub fn withdraw SOL. We need our lifetime specifier here. So now we're withdrawing SOL from the SOL account to the depositor. And since we're making a transfer from the SOL account, we defined the SOL account earlier as a PDA, so we're going to need the signer seeds for the SOL account to be able to process the transfer. So let's first define the signer seeds. We'll explicitly define this type. Okay. Now we're going to reference, okay. So this will be the seed for the SOL account. And then also the depositor key. Okay. And then we need the bump. So since we have the bump in our instruction, we're going to pass that through as an argument here. So we'll go back up to our function definition and add in the bump, which is a U8 type. Okay. Instead of passing through the entire depositor account here, we're just going to take the depositor key because we have that in our previous instruction. So let's do depositor key, which is a public key. And this we can just update to the depositor key as ref. There we go. And now we need to update our imports. So we want, okay, this was a weird import. We're going to just delete that. And now we want to use the crate for the seed SOL account. Okay, now that we have our signer seeds, we can actually write our transfer function. So we're going to import the transfer, and that is coming from import transfer. And because we're transferring SOL, it's coming from the system program. So we'll do system program transfer. There we go. And you can see the arguments that this takes in. So first we need the CPI context. Let's define that. And since we're signing with a PDA, we need new with signer. Okay. So the program is going to be the system program because we're transferring SOL, or Lampports actually. So the system program we've passed through as an account for the withdrawal instruction, so we're just going to pass that through this function. So it's a system program, there you go. And then we'll just convert this to account info. Okay. Now we can define our transfer. We'll import this struct from the system program. So we'll add in transfer. Okay. And now we just need to define from and to. So from, we can pass through this account. So this is going to be from the system account. And this is going to account info. Because our transfer is coming from the SOL account and going into the depositor's account. So from, we'll do from to account info, and then to, we'll do the same. There you go. Now, since we are using the CPI context with signer, we need to specify the signer seeds. So that will come right after defining the transfer. And then lastly, we need the amount of Lampports that we're going to transfer. So we'll pass through the amounts into this function. And that is a U64 type. Okay. And there's our withdrawal function. So we did withdrawal. Now we need to be able to burn. So the next function is going to be burning tokens. So pub fn burn tokens. Okay, so here we can just use burn. And because we're burning the stablecoin token, which is a token 2022 token, we're going to import this from token 2022. So import Anchor SPL token 2022 burn. And now since the mint account is its own authority and we're not signing with PDAs here, we don't need to define the signer seeds. So we can just use the CPI context new. And first we need the program, and since this is for the mint account, we're going to use the token program. So let's pull the token program from the instruction since we're passing that through our context for the redeem collateral and burn tokens instruction. So we'll add that to be passed through here, token program. And this is a program of token 2022. Now we need to update our import to include this. Okay, so now we'll just do token program to account info. Okay, and next we just need burn. So let's update our import to include burn. And actually, let's fix this import because our token 2022 should come from the token interface. There we go. Okay, so for our burn, we just have the mint, the from, and the authority. So our mint is going to be the mint account that's being passed through. We already passed this through our struct for our context, so we can just pull that in. So we'll do mint account, and this is an interface account. And we'll do info, and then token account. Okay. And we want to make sure we're using the token account. So this did an import from token, and we don't want that. We want the import to come from token interface. So we'll update this to token account. There we go. Okay. So the first field is mint, and we'll do our mint account to account info. The next field is from. And this is coming from the token account. So we're going to add in the token account that we passed through here. And this is an interface account for token account. And sorry, the mint account is not a token account, it's a mint. So let's fix that and then update the import for mint. There we go. Okay, so from, and this is the token account to account info. And then lastly is the authority. And then we're going to pass through the authority here. And that is actually the signer of the instruction. Okay. And now we just need to specify the amount of tokens to burn. So we can just write amount, and we'll pass through the amount into the function. Okay, so that's everything we need for burn tokens. Now we can take these two functions, pull them into our redeem collateral and burn tokens instruction, and we're good to go. So we check the health factor. So next we want to burn tokens. Let's make sure we import this, so we'll update our crate. Okay, and we'll check the arguments that we need, which is the token program, mint account, token account, authority, and amount. So let's update that. Let's make sure Copilot did this correctly. We have token program first, then we have the mint account, then we have the token account, we have the authority, which in this case is the depositor, and then we have the amount to burn. Okay, great. And then we unwrap that, and now we're good to withdraw SOL. So last function we want to import here is withdraw SOL. And we'll update our imports. Withdraw SOL. And now let's see. We're going to pass through the bump, the depositor key, the system program from and to an amount. So first we're going to get the bump, and the bump was saved into the collateral account. So we'll do context.accounts.collateral account dot, and we want the bump for the SOL account. So bump SOL account. There we go. Okay. Up next, we have bump, we have the depositor key is next. So we're going to do context.accounts.depositor.key. Okay? And then we have the system program. So we'll do accounts.systemprogram. And then we have the from account. So the from account is the SOL account. And then we have the to account, which is going to the depositor. So we're going to do accounts depositor, and we want to account info. Okay. And then lastly is the amount, which is the amount of collateral. And then we'll just unwrap this. Okay. And there's our function. So now we're going to take this function that we just wrote, pull it into our librs, and define the instruction that we want for our program. So we'll go back to the librs, And now we have pub fn, redeem collateral and burn tokens. We're passing through the context for redeem collateral. We're passing through the amount of collateral and the amount to burn. And then we're pulling in the process redeem collateral and burn tokens function that we just wrote in this file here. Okay. And then we're just going to clean up a few things. And looks like we're good to go for that. So before we do anything else, let's just make sure everything builds. So we're going to run anchor build here and make sure we have all of our instructions written correctly and everything compiles. Okay, so you can see all of our code compiled and everything built for our program. So now that our code compiled, we're just going to go over everything we have so far as instructions in our program. We have initializing and updating our config, and then depositing collateral, minting tokens, redeeming collateral, and burning tokens. So this is pretty much the main logic needed for an algorithmic stablecoin. There's one step that we're missing, and that is the ability to liquidate accounts. So if a collateral account becomes unhealthy, meaning the health factor falls below 1, there needs to be an ability for a liquidator to come in and liquidate the accounts. So we're going to write the logic for liquidations. We'll add a file in our withdraw folder for liquidate, and then update the mod file. Okay. We'll go back to our liquidate file. We're going to use anchor. And now let's think about everything needed to liquidate. So first we're going to work through all of the accounts needed because we're going to define the struct for our context. And that is going to process all the accounts needed to run the instruction. So let's do, as always, our derive accounts. And then we'll name our struct liquidate. Okay, so the first account we're going to pass through, this struct, is going to be the signer of the instruction, and in this case, it's going to be the liquidator. So we'll need an account for the liquidator. And that is the signer. Now we're going to need the price update from Pyth to be able to calculate the current price of the asset. So we'll do pub price update. And that will be the price update v2 from Pyth. So let's update our imports. That's coming from the Pyth Solana receiver SDK. And now we'll need the config account to be able to pull information like the minimum health factor. We'll add in the account. And since this is a PDA, we need to define the seeds. And we can just pull the seed for the config account from our constants. Okay. And then since we're stating the seeds, we need the bump. And that we save to the config account, so we can just load that in. And then next we're going to do one more check, and this is the same check that we've been doing, and it's just making sure the config account is using the right mint account. So we're going to do has one and make sure we have the correct mint account. Okay, and then we'll just name this account, so config account. And now we'll update our imports. So we need our seed config account constant, so we'll use the crate for that. We'll need to also pull in the config. And then the error for the mint account is that we haven't passed the mint account through the struct yet, which we'll do later. Okay, so next we'll need the collateral account, and this is to be able to get all the information for the specific account that we want to liquidate. So we'll add in account. It's going to be mutable because we're going to be changing the account. And then we want to make sure it has the SOL account. And this is our collateral account, and we'll have to import collateral. Okay. And then this error is just like the error above, meaning that we need to pass through the SOL account for it to have an account to verify against. Okay, so let's pass through the SOL account. And since the SOL account is holding LAN ports, it's just a system account. And then we'll need the mint account as well. So you can see once we pass through the SOL account, this error went away. And once we pass through the mint account, the other error should go away as well. And the mint account is an interface account with mint, and we just have to import mint. And mint is coming from the token interface. Okay. Now we need the token account from the liquidator. So we'll pass that through. This will be mutable, and it is an associated token. And the mint is going to be the same as the mint account. The authority is the liquidator, and then we need the token program. And that will pass through after this. Okay, so token account. And now we need the token program, which is token 2022, and then we need the system program. Okay, and then we'll update our imports. So for token interface, which is here, we're going to also need token 2022 and token account. Okay. There is an error in our account, so it looks like we did some account type incorrect. So let's fix that. So right here, the token account, it's an interface account, not just an account. And there we go. So that's our struct that we'll need for our context for this instruction. Now let's write the instruction. So we have pub fn process liquidate. We'll pass through our context. Make sure we don't have any typos. We'll fix that. Okay. And now we're going to allow the liquidator to specify the amount that they want to burn. So we'll add that as an argument as well. Now, before we allow the liquidation to process, we're going to want to make sure that the account is unhealthy and able to be liquidated. So the first thing we want to do is check the health factor. So we're going to check the health factor just like we did in the other instructions. So let health factor equal, and we're going to calculate the health factor. And we want to import the health factor calculation function from our crate, which automatically happened. Okay, so now let's see. We need to pass through the collateral account, config account, and price feed. So let's add that now. We need first the collateral account, so CTX collateral account, okay, config account, and price update. And then we're just gonna unwrap that. Great. So now we know what the health factor is. Now we want to run a check of the health factor. So we're going to require that the health factor is below the minimum health factor. If not, we want to return an error and let the liquidator know that they cannot liquidate the account. So require, oops. And we want health factor to be less than, and we're going to load in the minimum health factor from the config accounts. Okay. And if it's not, we're going to return a custom error, and it will be that it is above the minimum health factor. And then we're going to update our custom error. So first, let's import the custom error, enum. We're going to go to our error file and include the above minimum health factor error. So error rs, we're going to paste in the custom error we just created, and we're going to define the message. We'll say cannot liquidate a healthy account. There you go. And we'll fix our typo. There you go. Okay, so back to our liquidate file. So we did our check for the health factor. If the account's healthy, it's going to return an error. If not, we're going to go ahead and process the liquidation. So we're passing through the amount that we want to burn in its USD value. So now we need to be able to get lamb ports from USD to be able to use the lamb ports to calculate how much we want to liquidate. So before we actually process our liquidation, let's create a function to be able to get lamb ports from USD. So we have our lamb ports, which is what we need, and we want to write a function to get lamb ports from USD. So let's define that in our utils. We'll go back to our utils file where we were checking the health factor, and here we have getting a USD value. So we're going to do something kind of similar. We'll do get lamb ports from USD, and this is going to take in the amount in USD. So kind of the opposite of what we were doing above. And that is a U64. And then we need the price feed. And then our result is going to be in a U64 because we want the value of lamb ports. Okay, first we need the price. So we can actually take the same logic from above. We're getting the feed ID and then we're calculating the price all from Pyth. So we can pull that in. Okay. And now we'll do the same check. We want to make sure that the price is above 0. And now we're going to get the price in USD. And it looks like Copilot may have figured this out. So let's accept their suggestions and take a look. So we have the price in USD. We're taking the price from the price struct, casting as a U128, and then multiplying by the price feed decimal adjustment. Okay, now that we have that, we want to get the amount in lamb ports. So we're taking the amount in USD, casting as a 128 for precision. We're going to multiply by lamb ports per sol, and then divide by the price in USD. Okay, and then we return the amount in lamb ports. Great, so that's everything we need there. And now we'll go back to our liquidate function. We'll make sure that we're importing the get lamb ports from USD. Okay, and now we're going to check what we need to pass through. So this function takes 2 arguments, and it's the amount in USD and the price feed. So the amount in USD is the amount to burn, and then the price feed we can just pull from the price update account. There we go. And now that we have the lamb ports, we want to calculate what the liquidation bonus is that's going to be sent to the liquidator. So let liquidation bonus So this is going to be the lamports times the liquidation bonus, which we saved to the config account state. So we'll pull that in, ctx.accounts.config account liquidation bonus. And now I want to divide by 100 because the liquidation bonus is a percentage. Okay. Now we want to calculate the amount to liquidate. So the amount to liquidate is the lamports that we're liquidating from the account, as well as the liquidation bonus that's going back to the liquidator. So the amount to liquidate is equal to lamports plus the liquidation bonus. So now that we have that, we're going to be able to process our liquidation. So when we're liquidating, we want to be able to withdraw SOL from the account. We want to be able to burn tokens and then just update the collateral account state. So let's first withdraw the SOL. And then we'll update the import for withdrawal SOL. Okay. And this takes in the bump, depositor key, system program from to an amount. Okay. So we'll do the context.accounts dot. We save the bump for the SOL account to the collateral account state. So we can load in the collateral accounts and then get the bump for the SOL account. Okay. And then next is the depositor key. So we can just do context.accounts dot, and we saved the depositor to the collateral account. So we'll load in the collateral account again and then grab the depositor key that we saved. Okay. And then up next is the system program. So we can just pull that from the accounts. ctx.account system program. And then next is from. So from, it's coming from the SOL account. So we'll load in the SOL account. And then to, it's going to the liquidator. So we can just do ctx dot accounts dot liquidator to account info. Okay. And then we need the amount, which is the amount to liquidate. And then we can just unwrap this. And now I withdrew the SOL from the collateral account. So up next is just burning tokens. So we're going to burn tokens. And we're going to update the import for burn tokens. So the first thing we're going to pass through is the token program. And then the mint account. And then the token account. And then the authority is going to be the liquidator in this case. And then the amount is just the amount to burn. Okay. So now that the account has been liquidated, we're going to update the collateral account state to reflect these changes. So we can load in the collateral account, take a mutable reference, and then we're just going to update both the lamport balance and the amount minted in the collateral account state. So collateral account dot lamport balance is, let's change this a bit. It's just going to be the account dot SOL account dot lamports, and we're taking the lamports directly because the liquidation already occurred. So we're taking the current amount of land ports in the Sol account. Okay, and then next is the amount minted, and we're just going to subtract by the amount to burn. Okay, you can add an additional check for the health factor after the liquidation occurred just to log the new health factor to verify that it's healthy. It's not needed for the liquidation to process, but we're just going to do it to be able to have that log. So we'll do calculate health factor, and it's going to be the collateral account, so ctx.accounts.collateral account, and then the config account, and then the price update. Okay, and that is everything we need for the liquidation. So now we can go back to our librs and then add our final instruction for our program. So librs, and we can do pub fn liquidate. And we're going to take in the liquidate context, the amount to burn, and then we're going to use the process liquidate function that we just wrote in our previous file. We'll save that. Now everything looks good to go. So all that's left is to test out everything that we've written so far in our program and make sure that our stablecoin works. So let's build our program. We're going to run anchor build. And what this is doing, it's making sure everything compiles, but it's also updating our target folder. So if you go into target, you can see you have the IDL, you have these types, which is an IDL that is in camel case format, so it's compatible with TypeScript. You have a few other things like the .so of your program. So this is updating your target with the latest version of your program. Now that we have that, we're going to be able to update our TypeScript tests. So we're going to navigate to test, and we're going to go to stablecoin.ts. And let's start writing our tests. So the first thing we want to do for our test is to set up our environment properly. Let's see. We have our provider. So we're just going to change the way that everything is configured currently. So we're going to first make a const for our provider. And that is an anchor. We'll use anchor provider.env. There you go. And then we want the connection. So const connection. And we're going to need the connection because we want to be able to use Pyth. And a connection is needed to be able to import Pyth into your environment here. So connection, we're going to do provider.connection. And then we need a wallet. So const wallet is your provider wallet. But we want this as an anchor wallet. Okay. Now we can do anchor set provider. And we'll just set the provider with the provider. So we have our program, and then it's the anchor workspace for the stablecoin. And this is as the program of type stablecoin. And this is the type file that has been generated for the anchor IDL. So to be able to use the Pyth Solana receiver in our TypeScript files, we're going to have to update some of our npm packages. So first, we're going to npm install. And we need the Pyth network price service client. So let's grab that. So here is the npm package for the Pyth Solana receiver SDK. So we're just going to install this. And we'll go back to our VS Code and we'll run npm install. Okay, so from this npm package, we can generate a new Pyth Solana receiver. And we're going to do that with const Pyth Solana receiver. And this will be a new Pyth Solana receiver. Okay, and we want to import this from the package we just installed. So add import from Pyth network. Okay. And then this takes in, we want the connection, which is why we defined that earlier. And we also want the wallet. The rest of these fields are optional, so we're not going to add those. We just need the connection and the wallet. Okay. Now that we have the Solana receiver, we want to be able to use our price feed. So for our testing purposes, we're using the Sol USD price feed. So we're going to go back to our constants and take that price feed value. Okay. We'll go back to our TypeScript test, and we're going to create a constant in TypeScript this time for our price feed. So we'll do Sol price feed ID. And we'll paste in the price feed that we just copied from the other file. Okay. Now that we have that, we're going to be able to get the Sol USD price feed account. So we can just do const Sol USD price feed account. And we'll take the Pyth Solana receiver that we just created. And we're going to get the price feed account address. So get price feed account address. And we'll take in first the shard ID, which is just 0. And then it's going to take in the price feed ID, which we just defined above. And somehow I deleted that, so let's fix that. Okay, we're just formatting everything. There we go. Okay, so now we're able to get the Sol USD price feed account address. And now that we have that, we have pretty much everything set up for our environment, and then we can start doing tests. There's one last thing that we need, and that's to derive the PDA for our collateral account. So we'll do const collateral account. And this is, we're going to use anchor dot web3 dot public key, and then find program address sync. And this is going to find the address from the PDA. So we'll do buffer from, and our collateral account was defined as collateral, and then we also used the public key of the depositor into the collateral account. So we're going to do wallet.public key to buffer, and then all we have left is the program ID. Okay, now I think we have everything defined for our environment. We have our program, we have Pyth set up correctly for our Sol USD price feed, and we have the account address for our collateral account. Okay, so let's start writing our first test, and that's going to be initializing our config. So we can delete what was preset here, and we're just going to write our transaction. So const tx is equal to await program.methods. Oh. And we want to initialize config. Okay. So this takes in no arguments. We'll leave that blank. And then we'll just need to pass through the accounts, which we don't need to explicitly state any here. And then we'll add in the RPC. And we're going to do skip preflight true. And we're also going to do commitment confirmed. All right, so that is our first test. We're just initializing the config. The next test, we're going to want to deposit collateral and then mint our stablecoin. So let's write out that test. We're going to deposit collateral and mint USDC. and this will also be an async function. Okay. And now here, we're going to define both the amount of collateral and the amount to mint. So const amount collateral is equal to, and then the amount to mint. Okay, so now let's write out our transaction, and that is going to be await program methods, and then we'll call the instruction for deposit collateral and mint. And then we just have to pass through our two arguments that are needed, which is the amount of collateral and amount to mint. And since this is a U64, in TypeScript, we're going to have to use big number. So we're going to use new anchor.bn of your amount of collateral. And then the same thing we're going to do for the amount to mint. Okay. Now we'll pass through the accounts, and the additional account that we have to specify here is going to be our Sol USD price feed account, which we already generated earlier in our environment setup. We'll pass through accounts. This will be price update, which is our Sol USD price feed account. Okay, and then lastly is our RPC. I'm just going to copy over what we had in the previous step. Okay, and I also want to add in some console logs here just so we can see all of our transaction signatures. We'll just do your transaction signature. Okay, because then we can just copy this over into all of the instructions. Okay, so next test is being able to redeem collateral and burn USDC. So we'll do redeem collateral and burn USDC. Okay. So here we're going to specify the amount to burn and the amount of collateral. So in this test, we're just going to do half the amount. So we still keep something in the account. Okay. And then we'll do our program method to redeem collateral and burn tokens. We're passing through the amount of collateral and the amount to burn, just like we did above. And then our accounts is going to be the same thing. We're just passing through the price update. And then we'll do the RPC with skip preflight and the commitment confirmed, and then console log the transaction. Okay, next we want to update the config to then change the minimum health factor so this account becomes unhealthy and we can test the liquidation. So let's do update config. And we'll just define the transaction to update the config. So await program methods. Dot update config. So what we're going to pass through for update config is going to be the new value for the minimum health factor. So here we're going to make that 100. Okay. And then the accounts, we don't need to define any accounts here. And then we'll need to set the RPC. Okay. And then lastly, we're just going to console log And looks like I have a typo that I've been carrying over, so we're just going to fix that to your. Okay, there we go. So now that the config is updated, we should be able to liquidate the account. So let's test out liquidations. We'll do liquidate async, and then we're going to do our transaction program methods liquidate, and we want to define how much to liquidate. So here we'll just do 1. Okay. Accounts, we don't need the collateral account. We can leave this empty. And then we have the RPC, skip preflight, and commitment. And then console log. And there we go. That's our liquidate transaction. And then the last thing, we'll just update the config back to the normal minimum health factor of 1. So we'll just do update config. And this is going to be exactly the same as we did earlier, and we'll just change this to 1. So this should be everything we need for our test. There's a little bit more environment setup that we need. 1 second while we do that. So a few more things we need to update. Outside of our TypeScript file, after we wrote these tests, we also need to update our anchor toml. And that's because this TypeScript file is running the test with your test validator, and we need to make sure that we have the Pyth account cloned to your test validator. So we're going to make a few updates here. So we'll go to anchor toml, and then under scripts, we're going to define our setup for tests. So tests, we're just going to have a wait for the startup and shutdown. So we'll set that. Startup, wait. We'll just set that to 5,000. And then shutdown wait. We'll set to 2,000. Okay, and then we just need to define that this isn't upgradable. Okay. Now we want to define our test validator. So test.validator, and we're going to be using the bind address is just going to be (0.0.0.0.0), and then we'll need the URL. Which is just going to be mainnet. So we'll paste the mainnet URL for Solana. Okay. And then the ledger is going to be from your test ledger. So we'll do in our anchor, we want test ledger. Okay. And then we need the RPC port. We'll do 8899. Okay. And then one last thing is the account that we want to clone to our test validator. So we'll do test.validator.clone. And we'll state the address of Pyth. So let's get that. We can get that from Solana FM. So if you go to Solana FM and you type in Pyth receiver, you have here the program for the Solana Pyth receiver, and we want to take the address of it. So right here, we're going to copy that, and that is the address that we want to clone into our test validator. Okay. Now we want to update our package.json, and then we should be good. To get this to be able to run, we need the RPC WebSockets. So we'll npm install RPC WebSockets. Okay. And just for version compatibility, I know that this version works, so we're going to bump that down. One more thing we want to include is Web3.js. So it should be at Solana dash web3.js. Okay. And we're actually going to bump this down a little bit. We'll do 73. Now that we updated our Anchor TOML and installed all of our NPM packages, we're going to test out our TypeScript test that we wrote. So we can just run anchor test. And this is going to compile the program, deploy it, and test it. Okay, so we're getting an error with the liquidation, and looks like we didn't pass through the accounts that we need for liquidation. So we're going to go back to liquidate, and in the liquidate instruction, we need to pass through 2 accounts. So we need the collateral account, which is the PDA that we derived up here, and we never used it. So we're going to pass that through first. And we also need the price update to be able to calculate the current price. Okay, now let's test out our test. And now you can see initialize passed, deposit collateral and mint passed, redeem collateral and burn passed, update config passed, but we had an issue with liquidate. And the error is unknown action undefined. So let's go back to our liquidate and see what is going on. So actually it looks like we were liquidating just 1 for some reason, and that's not a large enough value. So we're going to liquidate. We're going to change the amount to liquidate here. So we'll make a constant, and we'll do amount to burn. And we'll set that to 500. Okay. And then we'll just pass that through for how much we want to liquidate. Oops. Amount to burn. There you go. And let's just check everything else. Let's check our values. So, okay, here we have the amount of collateral and the amount to mint should actually be the same value, and we're missing some zeros on amount to mint. So we'll update that and make sure that these are the same. So now we have the collateral, we're minting, we're redeeming collateral, and we're burning. And these should also be the same values. Okay, there we go. We lost some zeros along the way. So now I think we have everything updated. So let's run anchor test one more time. And there we go. So all our tests pass. You can see the config was initialized, the deposit collateral and mint USD. You have redeem collateral and burn tokens. You have update the config, liquidate, and then re-updating the config. And there's our test suite. So we now know that all of our instructions work properly as intended in our program. Going back to our librs, we have the ability to initialize the config, update the config, deposit collateral and mint tokens, redeem collateral and burn tokens, and liquidate. So all of these core functions implement the core mechanism to allow you to adjust the supply of the stablecoin and respond to changes in market conditions.